Lesson 6.2 is Principles of Probability. So we're basically just going to keep building on what we've done so far. Example 1. Suppose at Edina High School, 298 students study only French, only Spanish, or both. 115 study French, 209 study Spanish, but because those add up to being greater than our total students, there has to be students who study both. How many students study both? So I'll show you kind of how to do it without a Venn diagram and then with a Venn diagram, which I believe we've done before. So the number of French or Spanish is 298. Again, or is like the whole Venn diagram, kind of everybody we're looking at. The number of French is 115. The number of Spanish is 209. If you add 115 and 209 together, you get 324. Then the number of French and Spanish, so our overlap, basically we take our 324 and we subtract 298, and we end up with 26. We could also do this with a Venn diagram and look at, basically, try to draw some decent circles. French, Spanish, so we know that total French is 115 and total Spanish is 209. So then if we show this, we know that 209 plus 115 was our 324. 324 minus our 298 got us our 26. So then if this is 26, 115 minus 26 is 89, and 209 minus 26 is 183. So this is what a Venn diagram would look like for this situation. So I would actually probably solve it the way on the left, but if you wanted to draw a Venn diagram to see what everything looks like, that's what it would look like. If a student is selected at random, what's the probability he is not studying both languages? Well, basically we're looking at anybody not studying both. So the number of students studying French only, which was this piece of the Venn diagram, so that's 89. The number studying Spanish only is that 183. So we're looking at 89 plus 183 over our total students, which was our 298. And this is equal to 272 over 298, which simplifies to 136 over 149 if you divide top and bottom by 2. So what's the probability that a random student that you select will not be studying both languages? 136 out of 149. So now we have a pair of six-sided dice is thrown. And if the dice are fair, sorry, the dice got pushed over here, meaning like they're not weighted in some way, you assume you have an equal probability of getting each of the six sides. What's the probability that the dice show doubles or a sum less than 10? So we're looking for probability of doubles or a sum less than 10. We're looking at everything, all of our options here that have doubles or a sum less than 10. So if we look for that, here's all the possibilities. So doubles are going to show up on the diagonal here. 3, 4, 5, 6. And then we look for a sum less than 10. That applies to some of our doubles, but we've always already counted those. We've already counted those first 4 in our diagonal. We won't count them again. So we end up with Yeah, so we have 1, 2, 3, 4, 5, 6. And then as far as less than 10, let's see. This is less than 10, 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 then we hit 10. So it looks like everything here. So the more we work with this, you'll kind of see where the patterns show up here. Less than 10, less than 10. These are all good. These are all good. And by good, I mean less than 10. We're still counting those. This is 9. Okay, and so those right there are all the ones that are 10 or above. So now doubles or a sum less than 10. If we look, we've basically covered all of them except for these 4, meaning the total that are doubles or a sum less than 10 are 32, because I know there's 36 total. So the probability we roll doubles or a sum less than 10 is 32 over 36. Divide top and bottom by 4. This simplifies to 8 over 9. So now we'll look at what is the probability that the dice show a 7 or an 11. So probability of a sum of 7 or 11. So if we look for that, I'll just pick a different highlighter color. Maybe that nice purple? Sure. So let's see, let's find a 7. There's a 7. And this is kind of fun because it just has a pattern, goes on the diagonal. Those are all equal to 7. And the ones that are equal to 11, so that's 1, 2, 3, 4, 5, 6. The ones that are equal to 11 are right here. 6 plus 2 is 8. So the probability that you get a sum of 7 or 11 is 8 over 36. Divide by 4 on top and bottom. This simplifies to 2 over 9. The addition counting principle, which is for one event only. So like you do one thing, like you roll dice once. This is finite sets. It applies to number and it applies to probability. Keep in mind that this U means union, and this is our OR. And this is intersection, kind of looks like an N. And this is our AND, which is the same as our overlap. So these formulas, basically the number in A or B is equal to the number of A plus the number of B minus the number in both. So you're subtracting out the overlap so it doesn't get double counted. That's essentially what's happening. Probability is the same. Probability of A or B is probability of A plus probability of B, and subtract out the overlap. So I'll show you how this works. So sorry, the alignment got weird, or the margin. So example 3, 2 fair-sided dice. Fair 6-sided dice are thrown. If A is rolling a 2, let's find the probability that you roll a 2. So there's actually only, let's see, how many ways can you roll a 2? Oh, I'm sorry, rolling a 2 on the red die. Otherwise, I'm like, it doesn't add up to 2. 2 on the red die, that's all of these, okay? 1, 2, 3, 4, 5, 6. Sorry, your notes are not in color. Basically the left die. Probability of A is 6 over 36, which simplifies to 1/6. Probability of rolling doubles, we have 1, 2, 3, 4, 5, 6. So probability of B, this was probability of A, probability of B is also 6 over 36, which simplifies to 1/6. So the concept of mutually exclusive means they don't have anything in common. So we're just going to write that. Or no overlap. So that's what mutually exclusive means. So are A and B mutually exclusive? And the answer is no. And that's because right here, this dice roll is in both events. So it's in A and B. So they're not mutually exclusive because this one where it's 2, 2 is in both A, oops, I forgot an H, and B. So mutually exclusive is there's nothing in both events or there's no overlap. So if you look here, the number of A and B, that's going to be the number of overlap. So the number of 2 on red and doubles. That was essentially what we circled twice. So it was just one. It was just this one right here. And this just says number. How many? 1. Probability of A and B. So probability of 2 on red and doubles is 1 out of all of the different dice sets that you could roll. So that's 1 out of 36. So now we're going to find the probability of A or B. And this is where that formula comes in. So the probability of getting 2 on red or doubles equals the probability that you get a 2 on the red die plus the probability you get doubles minus our overlap. So probability of 2 on red and doubles. And so this is this formula up here. So we add the probabilities together and subtract out the overlap. So here, probability of 2 on red or doubles is going to be, so probability of A or B. Our probability of A, we had that up here, was 1/6, plus probability of B was also 1/6. Subtract out our overlap, which was done over 36, and now we'll put them back in terms of 36s. This is 6 over 36 plus 6 over 36 minus 1 over 36. So the probability of A or B, a 2 on red or doubles, 6 plus 6 is 12, minus 1 is 11. So our probability is 11 over 36. It's another theorem, who cares, but basically what we know is that the probability of not A is going to be 1 minus the probability of A, or whatever that event is. Basically, it's going to be 100% minus whatever our probability was. That's what the 1 comes from. And this has to do with a complement. A complement is basically if you add two things together, you get the whole sample space, or you get 100%. So 2 fair dice are tossed, probability of not rolling doubles. Well, we know the probability of rolling doubles was 6 out of 36, or 1/6. So then the probability of not rolling doubles is going to be 1 minus that. 1 minus 1/6 is 6/6 minus 1/6, which is 5 over 6.